Hello，哎，我们开始上课哈。Okay, so I think we'll continue with the multivariate methods for parametric classification. Okay, 我们开始上课。Okay. All right. So again, a little bit repeat, right? So in a machine learning, what you take is take samples, you represent it as features, learn a mapping function to help you do either a classification, take an input into one of the K categories, or make it a regression, so it outputs a numerical values. Okay, so now we talk about in all previous sections we're talking about when there's input only one feature. So you know how to model that as a statistical Gaussian distribution. Okay, we know a statistical distribution for a single or that's fine. 全部这样也是有点难上，你看看。对 ，OK。That's fine. I'll try my best. Okay, so a single variate Gaussian distribution. But in reality, when we have machine learning experiments set up, usually there are multiple features. So we call them multivariate data, multiple measurements. You can gather from different sensors, or practically you can take one samples and represent them using multiple features. Right? In our previous example, you want to do high risk versus low risk classification. You take savings and incomes. These are two variables, right? So it's not a single variable stuff. So in reality, oftentimes you have a lot more measurements, or we call features or representations. Okay. So in that case, where instead of having one single input, we have D inputs, okay, features or attribute, whatever you want to call it, and then we actually get n samples of those D features. Okay. So again, the idea is simply extending, in a parametric classification, you're extending the single Gaussian distribution, extending that to multivariate normal or multivariate Gaussian distribution, or multivariate normal distribution, right? So if you have, two features, right, this will be, the PDF for two-dimensional Gaussian distribution. Okay, so when you have multiple, right, it's not just two. You have some d-dimensional variables. You're extending your Gaussian distribution to d-dimensional Gaussian distribution. Okay, so again, a lot of the concept about discriminant function, parametric classification, learning the parameters. Once you learn the parameter, use it to do inferences. All those process of machine learning is the same. Where in this section, only thing we're changing is saying, okay, when you have input that's not a single variable or single number, single features, you have multiple features, how would you change? Okay, the simplest way to change, right, is take a single variate normal distribution to a multivariate normal distribution. Okay, so now you're just saying, now my X distribution is a d-dimensional Gaussian distribution, okay, with two sets of parameters, right? One is a vector of mean, okay, another is a covariance matrix. Okay. So the PDF now just becomes this particular form, okay, 1 over square root, not square root, like it's basically d over 2, 2 pi to the d over 2, the determinant of the covariance matrix, take it to the square root, an exponential minus 1/2 x, right, the feature vector, right, minus the mean vector transpose times the inverse of the covariance matrix, x minus the mean vector, and then just multiply. Okay. So look at this. Look at this distribution. Essentially, what you need is this and this. We call the new parameters. Okay. So mean now is a vector. Okay. In a single variable, it's a single number, right? Now it's become a vector because you have a d-dimensional input. Now the covariance, okay, are xi, xj, I, and j indicates which feature dimensions that is. So the covariance between xi and xj give you sigma ij. Okay. The correlation is just that sigma ij divided by sigma and sigma j. Okay. So the covariance matrix, if you write it out, actual, probabilistic form, the expected value of x is your feature vector minus mu is the mean vector, x minus mu transpose, basically some square form, right? And then you take the expected value. Okay, so again, this definition you should have learned it in your probability. Okay, we're just extending that into a multi-dimensional space. So it's actually a matrix. On the diagonal, these are the variances of individual feature dimensions. On the off diagonals, it tells you the covariance between the feature dimensions. Okay, so that construct the entire covariance matrix. 好，我这边还是很快带一下哈，在这个 section 所有问题跟之前的问题一样 ，setup 都一样啊 ，machinery setup 都是一样 ，train test、train development test，OK，、你有了一份 data， 你想要做 classification，OK，、我现在要把它用 Bayesian decision 方法去做它，所以我需要一个 P of x given ci，OK，、那 P of x given ci 是一个几率分布 ，OK， 因为我没办法真的知道每一个 x 相对应的几率是什么，所以假设一种分布，这个分布会有参数。所以就 parametric classification 这个道理出来，这个 parametric method 道理出来，因为我假设它成一种分布，所以我如果要真的算出这个几率，我只要知道参数，我只要知道这个参数，把 x 带进去，我就可以算出几率。OK， 这个道理是一样。那这边我们只是把它延伸了，然后你的 feature，OK，P of x given ci， 那个 x 可能不是只有一个维度，可能有多个维度。OK， 你做任何辨识，你可能不是只是拿，对，你想要辨识一个男生女生，可能不是拿头发长或短嘛，你可能还用别的特征，眼镜啊。等等穿衣服啊，所以你有很多的 feature 可以来辨识一件事情。那你的 feature input 本身变得低维度的时候，我们一个很简单的 extension 就是把这高圈 distribution 从一个维度变成多个维度。OK， 就大概概念上是这样。所以我们的 P of x，x 现在是一个 vector。OK， 现在说它其实是一个 d-dimensional 的高圈 distribution。OK， 那高圈 distribution 在 d-dimensional 其实也还是只有两组参数。OK， 一组就是还是它的 mean。OK， 另外一组就是 covariance。OK。那就这两个 ，OK， 好，那 mean 就是 expected value of 这个 x，OK，、那就是一个 mean vector 啊，m1 to d，OK，i、to d 代表是那低维度的 feature， 每一个 feature 最终它都有个 mean 值 ，OK， 或是一个期望值啊。当我们要去知它的参数，我们会用 data 去估这个参数应该长什么样子，那就是 learning 的部分 ，OK。那 covariance 是一个 matrix，OK，covariance、是 expected value of x minus mean。x minus mean take it to the square。看看这个其实它就是也是一个像是 variance 的 term 嘛 ，OK， 只是说你现在有多个维度，所以它会去计算 off diagonal， 就是说它每 feature 跟 feature 之间的关系，它也会在这 covariance matrix 里面把它记起来 ，OK， 所以它其实 covariance matrix 在 diagonal 向上就是你那一个 feature， 第一个 feature 它的 variance， 第二个 feature 它的 variance， 第三个 feature 到第一个维度的 feature， 在 off diagonal 跟你算就是 covariance，OK，、就是第一个 feature 跟第二个 feature 之间关联性。第一个 feature 跟第三个 feature 之间关联性等等，第一个 feature 跟第一个 feature 之间关联性。OK， 所以这是个 covariance covariance matrix。Okay， 这些就是参数。OK，these、are the parameters needed for multivariate Gaussian distribution. Okay. Let's look at simple case, right? Multivariate normal distribution in 2D, right? Let's introduce a concept called Mahalanobis distance. Okay, a distance. Think about what the distance tells you. Okay, again, the name of the distance means how far are you from somewhere, right? So we have a measure of how far away from you from somewhere. So we're measuring x, right? The data minus some mean. Okay, take it to the square, right? Because this is transpose times x minus mu, right? It's basically some square distance weighted by the inverse of the variances, right? So we call this a Mahalanobis distance. Look at this term, right? This term and then this term are essentially the same term. Okay, so Gaussian distribution essentially is a weighted version of Mahalanobis distance. Okay, so this is you can imagine this is a distance function. Okay, so Mahalanobis distance is measuring the distance from x to mu in terms of sigma, normalized for different variances in variances correlation. So here's it uses a inverse, right? The larger variance adds to less distance, and correlated variables also contribute less to the distance. Okay, so again, imagine you have x, right? You want to measure how far away from you from mean, but originally, if this distribution is very widespread, even if I'm very far away from you, that maybe means I'm also close. Okay, if you have a distribution that's very concentrated, okay. Even if I seems like I'm not so far away from you because it's so concentrated, I may also be actually far away from you. So this variances tells you the underlying. It's basically a distance measured by underlying variance of the distribution. Okay, so that's the Mahalanobis distance. It's basically the distance that's used in the Gaussian distribution. Okay, so if you have d equals 2, your covariance matrix behaves like this: sigma 1 square, sigma 2 square. rho sigma 1 sig 2, rho sigma 1 sig 2, and this p of x1 and x2 again boils down to this particular form. Okay, so this is a 2D normal distribution. I think what I really want to emphasize is this Mahalanobis distance. Okay, this is kind of the key in terms of measuring, right, how far away from you from a particular point. Okay, 好，我这边稍微讲一下。那这边只是举例说，如果我是个 2D 的话，最后就长这样。那这个过程中，我们 introduce 一个概念，叫做这叫 Mahalanobis distance。OK， 这个 term x minus mu，OK，x 跟 mu 之间的距离嘛。OK， 那它是 vector form， 所以有 transpose， 上没有 transpose 其实就是 square 嘛。OK， 所以其实在讲的是个 square distance， 但是它乘上了一个 covariance 的 inverse， 对 ，covariance inverse。所以为什么要乘上这个？因为我如果没有这一项，就只是很单纯的欧式距离，我跟你离多远 ？OK， 那这个 square 的距离离多远 ？OK， 我乘上这个 inverse 项的时候，就会根据我其实这一个 x 它本身的 distribution，OK， 如果很大 ，OK， 我如果很大，那我会摆在它的 inverse 项 ，OK， 所以我 variance 很大的时候，我其实 distance 加的很少。你可以想，这个其实蛮直观的吧？因为我如果一个 x 本身分布就很广泛 ，OK， 所以就算两个距离很远，那其实也是很有可能的，所以我距离其实没有算这么大。我如果一个 x 它本身它可以分布的空间就很小 ，OK， 我就算离你很近，可是也不算真的很近 ，OK， 因为你本来就没有办法离我很远，你本来就离 me 没有很远的，所以我就算离你很近，可能其实还是很远 ，OK， 所以透过 introduce 这个 inverse 这个项 ，OK， 它可以来去 reweight 到底在分布上我的距离离你多远 ，OK， 而不是单纯的只是点对点的距离，而是有考虑分布本身的变异性来去考虑我跟你之间的距离 ，OK， 这个Mahalanobis，如果你看到这个 term， 它其实就跟高旋 distribution 的这个 term 其实是一样的嘛，对，还在看我跟你之间的距离 ，OK， 然后 take exponential 项再乘上某一些。这全部都是 constant 嘛 ，OK， 这是 2 pi d to 2，OK， 这是一个 constant， 这些是 constant，constant 乘上 exponential 的 Mahalanobis distance， 其实就是高旋 distribution，OK。Alright, so that's back to the parametric classification. Okay, once we know that, right? So again, repeat. The reason we're doing all this, complicated math is basically we want to do parametric classification. We want to do some classification. We want to have a way to model P of x given Ci. In Ci classes, what's the probability distribution of P, so that we can input that to our Bayesian distribution rule, input that using our discriminant function, right? So now we assume that this probability distribution is normal distribution with mean, right? Mi, right? This is a vector. So a vector of mean for each class, a covariance matrix for each of the class. Okay. So again, P of x given Ci is this particular form. So the discriminant function, right? Log of P of x given Ci plus log of P of Ci. Now we just write it out, okay, in terms of this equation. So the discriminant function, basically every x input in for each of the classes is going to give you a number. Okay, how do we generate that number? Minus d over 2 log 2 pi minus d over 2 log the determinant of this covariance matrix minus 1/2. Right, then Mahalanobis distance, right? X minus mi transpose. Okay, the inverse of the covariance matrix of that class, x minus the mean of that class plus the prior distribution of that class distribution. Okay, log of P Ci. Okay, so again, once you're at this point, right, you have a function you can write at testing to do classification. Okay, what's really missing now is you don't know what that covariance matrix is. Okay, and then how do I estimate mu I? Okay. Okay, so again, we're back to this the MLE estimation kind of thing. So it's again very similar to the single dimensional stuff. Okay, so the mean the mean vector for so in this slide there's some notation misleading actually. So I want to also add a little bit footnote here. So the I and j here indicates each dimension. Okay, the previous I here indicate which class it is. Okay, so just keep that in mind. There's a little notation misleading here. Okay, so the mean is very simple. Okay, sum up all the samples you have collected. Okay, divide by n. Okay, then you get a mean vector. Okay, it's the sample mean. That's the average. So you go out, collect data. Each data has d-dimensional features, and then you just you just average them. Okay, that becomes your mean vector. Okay. Now, how do you generate a covariance matrix? So just basically Sij equals to the ith dimensions of the t sample minus the ith dimensions of the mean values, jth dimensions of the t sample minus the jth dimensions mean value, multiply times over sums over n sample divided by number of samples you have an estimate of the covariance matrix. Okay. Then if you normalize by the individual Si and Sj, you get a correlation. Okay. So again, we're not going to derive this, but you can look at this very simple. It's the same thing as what we did in the previous single variate cases. Okay, so just put it together, right? So now you have each class is, so you're implementing a discriminant function. Each class you need a covariance matrix. Each class you need a sample mean vector. Okay, you go out and collect data. The data will tell you this data has d-dimensional feature. It gives you an Ri of t. It tells you whether this particular t sample belongs to ith class. Okay, so what you need to do first, you compute the prior distribution of that class, right? Sum over all samples, whether that t sample belong to ith class. Sum multiplied by n, you know proportionally how many samples belong to n class, belong to ith class. Okay, the mean vectors for the ith class. Look at the vectors that belongs to the ith class, right? Tth vector multiplied by 1 or 0 indicator function, whether this t sample belong to ith class. Sum it up, divide by number of samples that belong to the ith class, then you get this thing. Okay. Again, the ith class covariance matrix, you just need to multiply by Ri of t, divide by number of samples that are coming from the ith class. Once you've done this, you get the final implementable discriminant function. You can use it to do inferences. Okay, to do classification, right? So gi of xi tells you which class that is, x sample that comes in. You know si, you know mi, you know si. Take it inverse, put it all together. You get a number of this. Now go through all the classes and pick the one that gives you the largest value, and you're done with your classification. 好，我们再讲一下，这边 notation 有一点乱，所以我跟大家稍微讲一下。其实到这边的 I 其实都代表是哪一个类别了 ，OK？ 那只在中间这一块说，这边的 I，OK？ 我们要改，但它因为这是图示哦，那我就懒得重打，我直接写在旁边哦。这边的 I 其实是那一个 feature 的维度 ，OK？ 所以 IJ 是 I 跟 J 两个不同的 feature 维度 ，OK？ 所以你一个 vector 第一个维度、第二个维度，第一个 feature、第二个 feature、第三个 feature、第四个 feature，OK？ 那这边是等于是说我刚才讲。我们做 discriminant function 是为了做辨识嘛 ，OK？ 是为了 apply Bayesian decision rule 来去最后执行我的 classification。所以我如果知道这行公式，我就可以做一个辨识任务。但是我因为没有这个 Gaussian distribution 的这一个 covariance matrix， 我也没有 mean vector，OK？ 所以我需要透过去收一大堆资料来，我要去把这些参数给学出来 ，OK？ 那就是 training 的部分 ，OK？ 我需要 train 出这个参数应该要是什么。train 完之后，我就可以真的执行一个 machine learning 的辨识任务，我就用这个公式去带 ，OK？ 所以中间这些这个 MLE estimation 都在做 training，OK？ 那这边 training 看起来很简单，因为其实它是数学导完你就结论就结束 ，OK？ 那当然越复杂的 machine learning 模型，这个 training 就越复杂 ，OK？ 不过目前来讲，这些 training 都是只是我公式写完，我带进去，我其实就结束了 ，OK？ 那带完之后，我就会有那个 covariance 跟 mean。OK，covariance 跟 mean vector 我就可以带进这个公式。那这边一样 ，OK， 你可以想想，它去对比一维度的Gaussian distribution， 它其实样貌是很像的。OK， 只是我们现在变成一个 vector 或变成一个 covariance matrix。OK， 这个 POCI 跟你讲 ，OK， 每一个特定类别它的就是前期的 proportion 的 distribution 是多少？它占就是说 high risk 跟 low risk， 可能 high risk 本来就只占整个 population 里面的40%，low risk 可能60%，我男生女生可能就50%，这我们怎么知道？我们可以收 data， 然后去看，你的类别1占比多少，类别2占比多少，把它写出来，数学公式就这样算就好。我有一个 indicator function 跟我讲第一个 sample 你是不是跟 ith class 是同一个，如果是就1，如果不是就0，然后把这个全部加总就会跟你讲 ，OK， 那我 total 有多少笔资料是属于 第 i 个 class，OK，、那这样子除上你 total 收了多少 training 资料 ，OK， 那就会有一个比例出来嘛，这个比例就可以当做是 POCI，OK，、那我要算出第 i 个 class 它的 mean vector 一样，因为我其实要怎么算出 mean vector，OK，、我们刚才前面讲，其实你就是把 data 拿出来 ，OK， 然后去平均嘛 ，OK， 所以我要对第 i 的 class 怎么把那些 data 拿出来做平均，就是看 x 去乘上一个 indicator function。每一笔资料乘上你是不是来自那 i 个 class 的资料，加总起来除上你有多少资料来自那个 i class，OK，、那是平均嘛 ，OK， 所以你把 i class 资料拿出来做个平均，就是你的 mean vector。covariance matrix 一模一样，你有多少笔资料来自 i class， 你对它做 covariance 的 estimation，OK， 乘上 OK， 我只针对第 i 个 class 那些资料拿来去做这件事情 ，OK， 那就做个平均，你就有 covariance matrix。OK， 好，所以你看这所有项都是你收 training data 的时候会有的，对，你会有 x， 这是你收的资料，你会跟我讲这笔 x 来自哪一个类别，所以你会有答案 ，OK， 所以你就会有这个 indicator function， 所以这所有的东西在你的 training 资料里面都会有，有了你就用 MLE estimation，MLE estimation 完之后你就会有这些数值，然后这些数值拿来去估mean vector 跟 covariance matrix， 那我就把它替换掉就好了。OK，mean vector 跟 covariance matrix 把它换成我从 training data 学出来的 MI 跟 SI。OK， 那我现在这 discriminant function 就是 operationable。OK， 我就是确实可以用这个 discriminant function 来做 parametric classification。OK。Alright, so now we have, in a multivariate sense, when doing classification, we're doing multivariate classification. We're taking an approach that these features are Gaussian distribution, multivariate Gaussian distribution. Then we can do MLE estimation to estimate what the parameters are. Once that's learned, okay, then you implement a discriminant function. Things are complete. Okay, now the rest of the lecture I want to talk about is this thing. Okay, the covariance matrix. Okay, if you look at this this discriminant function, everything looks fine. Okay, except sometimes there's an issue here. Okay, the SI here. Okay, so there are a couple issues. Either in terms of computation. Okay, SI inverse. Okay, inverse of a matrix. Okay, usually takes a long time to compute. Okay, sometimes you may not be able to find the inverse if their rank is smaller than the row number, right? So I think that's linear algebra. So not all matrix has an inverse. Okay, and the reason really why, because if you have features and features that are very highly correlated, okay, that means one of the features are linear combination of the other one. The matrix collapse. The rank is smaller than the row number. Okay, then the inverse cannot be found. Okay, so there are a lot of little sort of numerical linear algebra issues when you do things working with the inverse of a matrix. Another thing is, if you look at this inverse of this covariance matrix, it's this complete matrix. So every one of this is a parameter we need to estimate. Okay, so think about the issues when you have, say, not too many, 100 features. Okay, per class. Okay, okay, so you have two classes, 100 features. You have at least 100 by 100 matrix of values. Okay, these are parameters you need to estimate. Okay, the parameter space starts to become really large. Okay, so that's also another issue. Okay, so when you deal with multivariate methods, okay, it's intuitive that we want more features. When you add more features and you want to do parametric classifications using a sort of a Gaussian distribution type of approach, things become a little bit hard. Okay, that's where we need to deal with this. 好，我这边再继续往下讲，往下讲之前，先讲概念哦。前面到这边其实没有新的 material， 我想跟大家讲，然后这边都是一样。OK， 那在 multivariate 的 parametric classification 里面 ，OK， 大部分之后他们在解析就是这个 SI 的问题。OK， 就是每一个类别它有一个自己 covariance matrix。OK， 那这边有两个问题，小问题啊，也不小啊，其实相对比较大。第一个是这个 inverse。OK， 那大家都学过 linear algebra， 解 inverse 不是一件非常容易的事情。OK， 就算解得出来，其实它还是蛮久的一件事情。OK， 它的 operation computation time 其实是蛮久的。OK， 那 inverse 最常解不出来的问题是什么？就是你的每一个 row 之间，或者每一个 feature 之间，它其实有高度关联性。OK， 所以我可能有一行的 feature 叫做男生，有一行 feature 变成叫女生。OK， 那这个 inverse 你一定解不出来，因为男生跟女生是 linearly 的直接相反。OK， 所以当你有2组 feature， 它的 correlation 几乎是1的时候 ，OK， 你的这个 covariance match 你就会解不出 inverse。OK， 所以这个 inverse 就会有很多的问题在里面。OK， 第一个 inverse 不好解 ，OK， 解得很慢。OK， 再来就是就算好解哦，解的也还可以，它的问题是它的 parameter 数蛮大的。OK， 就是这边 OK。我随便说刚才讲的2个类别，我就要做个2分法。OK， 那我每一个 input 假如说就100维 ，OK， 其实也不是很多，我随便算一算就可以算出100维 ，OK。那我这边就至少100乘100就乘个2个类别 ，OK。这么多的参数需要估 ，OK。那你想想看，我如果一笔资料估一个，当然简单的统计嘛，你不太可能一笔资料估一个参数，你好几笔资料估一个参数嘛 ，OK。我现在就已经有100乘以100 ，OK， 再乘上2 ，OK， 你随便就已经上万了 ，OK。那这还是只有2分法，用的很简单的 feature， 很简单的2个维度的东西 ，OK。所以我如果事情复杂化一点 ，OK， 这个维度很快就爆掉很大 ，OK， 就涨得很快很多，那你的 data 要收就非常非常多 ，OK。所以那运算又变得很复杂，那这个矩阵如果开始变得很大，大家都手解过550的矩阵 ，OK。如果你是算一个500乘以500 ，OK，10000乘以10000的 inverse，OK， 请问一下怎么解 ？OK， 所以这个 inverse 在这个 process 里面开始变成一个很令人困扰的事情 ，OK。So people start to make some modification or simplification, okay, in terms of doing this discriminant function. All right, so again, you'll start to think about that. If we work out different SI, okay, then it'll give a different form of that discriminant function. Okay, so the complete form is this. We know, okay, 1/2 log of something. Okay, we can rewrite this. Okay, again, I won't go through the whole rewriting issue, but you can rewrite this as x transpose wi x plus some wi vector transpose x plus a constant term. Okay, this wi is a inverse of a individual covariance matrix. Okay, this wi is a inverse of a covariance matrix multiplied by individual classes mean vector and the final constant term of these. So basically, you can rewrite this discriminant function as a quadratic term. Okay, some square term plus a w times x is a slope term, right? First order term, and some constant. Okay, it's a square second order, first order, and the constant term. Okay, so this discriminant function can first be rewritten as this quadratic form. Okay, so if you are familiar with MATLAB or Python, okay, there's a function called quadratic discriminant classifier. That's this. Okay, so if you want to implement quadratic discriminant classifier, you don't really need to write all this thing. You just call the MATLAB function quadratic thing. It's basically this function. Okay, and what it does, it basically says, okay, I'm going to do a parametric multivariate Gaussian distribution based classification. Okay, and then it's try to implement this function for you and try to do classification there. Okay, just keep it in mind. Now this is the full form. Okay, so you have probability x given c1 like this. Okay, probability c1 given x, right? So x1, x2. These are two different. Sorry, this is c2. I think this is c1, and then probability of c1 given x is this thing. So you have probability of c1 given x equals 0.5 is this line where you separate these two distribution. Separate these two distribution. You cut it here. Cut it here. Okay. So this is a Gaussian distribution for c1. This is a Gaussian distribution for c2. Anything beyond this line, we call it C1. Anything beyond this line, we call it C2. Okay, that's a very simple method. Okay. Now we can start. Making some simple assumptions. Okay. First, we can assume. Okay, when you have two classes, each one has an SI, right? So their covariance matrix, have its own covariance matrix. Okay, one is looking like this, one is looking like a tilted like this. Okay. What if they have the same covariance matrix? Okay, just assume. Okay, you don't know, you just assume they are. Okay, assume they have the same covariance matrix. How do you assume? You can say, okay, they share the same covariance matrix. Okay, so how do we get that? So some prior proportions probability of you coming from CI multiplied by your actual CI that's SI that's being learned from your data. And sum over all classes, and all the classes use the same covariance matrix. Okay. Okay, this is first simple deductions of a covariance matrix. Now your discriminant function start to reduce, okay, into this particular form. Gi of x, 1 is 1/2 x minus mi transpose si, s minus 1, okay, inverse of s. There's no longer an I term here, okay, because all the classes share the same covariance matrix. So it's a single covariance matrix for all classes, x minus mi log p of ci. Okay, so the discriminant function now can be reduced into a linear form. Okay, g of x, wi transpose x, wi and wi naught, where this term, the slope term, is just that particular inverse times individual classes mean vector and some constant term. Okay, so by assuming your every classes of your classification label, their data come from the distribution that have the same covariance matrix, your discriminant function reduces to a linear form, to a linear we call it linear discriminant function. Okay, so if you, again, quadratic discriminant function assume every class label has its own covariance matrix. If you share that covariance matrix across all labels or datas, then that reduces to a single, so a linear discriminant function. And you know, again, still this is line is separating the two. Now we're saying, okay, I'm going to use the same covariance matrix to model the distribution coming from these two data sets. Okay， 好，这边稍微讲一下，概念上好像有点抽象，但我想跟大家实物上其实不会啊。OK， 你原本就是要做分类法 ，OK， 你就是有2群资料哦，一群来自这个类别，一群来自这个类别。你说这一类别是一个高线 distribution， 这一类别是一个高线 distribution， 所以你个别估出了它的 mean 跟它的 covariance， 这边也估出了它的 mean 跟 covariance，OK， 各自有各自的 mean， 各自有各自的 covariance matrix。然后我的 discriminant function 就在这个2个中间画一条线啊，画哪一条线？画这个 posterior distribution 会是在 0.5， 如果小于 0.5 就是另外一个 class， 大于 0.5 就是这个 C1 这个 class。OK， 很简单的一个二分法嘛。OK， 那在那个情形下，你可以想 ，OK， 我其实假如说我的 data，OK，C1 这个 class data 就分布在这边 ，C2 class data 就分布在这边，我去收 data 就是长这样子。OK， 那它如果各自，我觉得说你就是自己的高线 distribution， 你的 covariance matrix 就是你独有 ，OK， 你的 covariance 就是你独有 ，OK， 所以它2个 covariance matrix 长得不一样，它的 mean 一个在这边，一个在这边 ，OK， 它各自有各自的 mean， 各自有各自 covariance matrix， 我画一条线把它切开来 ，OK， 那这条线的 discriminant function 就是我们刚才讲的这个 quadratic， 就是这 quadratic form， 那怎么来？其实就是这个 gi of x， 我只是把它重写而已，重写成一个这个有2次项的这个 quadratic term。那我们可以做个很简单的假设 ，OK， 我可以说，其实有可能这2群资料它背后的 covariance matrix 是一样的，它只是可能 mean 不一样而已，它来自2个高线 distribution， 但是2个高线 distribution 可能它的 covariance 是一样啊 ，OK， 那这个假设怎么来？你其实也不知道 ，OK， 你就觉得它应该要是哦，有可能只是因为你觉得我都是这些 feature 因为我都收同样的一些 feature，OK， 因为我每笔资料的 feature 是值不一样嘛。所以我可能这些 feature 就都是一样的东西啊 ，OK， 它或许背后的 covariance matrix 的结构应该要是一样 ，OK， 我没有必要每一种类别 ，OK，high risk 跟 low risk 它 covariance matrix 它还要不一样哦，因为 covariance matrix 代表是什么？代表是我去探讨这些比较多维度里面的每一个 feature 跟 feature 之间的 correlation 嘛 ，OK， 或许这件事情在不同类别下它其实是同样的啊，因为我 feature 是一样的 ，OK， 你可以做这个合理的假设 ，OK。是不是真实的不知道，但是它是个合理的假设 ，OK， 就是说我因为都是收这些 feature 本来就是只有这些 feature， 我收这个类别、这个类别、这3个类别，我收这3个类别我都是收一样的 feature， 这3个类别都是一样的 feature， 那当然这3个类别我可以假设它是同一种 covariance matrix， 我就不要个别类别有自己的一个 covariance matrix，OK。那这个做法最简单可以怎么做？你可以先每一个我先估出它自己的 covariance matrix， 我再去乘上它那个类别占比我说我 training data 里面的权重 ，OK， 那我就可以设定一个新的 S，OK， 这个 covariance 的 matrix 只有一个 ，OK， 用在每一个类别里面它的高线 distribution 要用的那个 S， 我都用同一个 ，OK， 那我就不会有 S subscript I 了 ，OK， 就是每一个都是 S。OK， 那我的 discriminant function 就可以重写。discriminant function 重写，它其实就变成一个 linear discriminant function， 它只有一个 slope 项乘上你的 feature，OK， 加上一个DC term，OK， 那重写样态长这样。 OK， 那一样，因为你假设它是一样，所以它 covariance matrix 就势必 OK 变成一样嘛。OK， 两群的资料它 covariance matrix 变成是一样的。那我线还是切在这边。OK， now we can make additional assumptions. OK， if you assume xj, j indicate which features they are. If you assume all the features are independent, okay, again, how? You don't know, you just assume. Okay, assume all the features are independent. Then your covariance matrix now becomes a diagonal matrix, right? Because here, repeat, right? If all the ij's are independent, then all these terms are zero, right? Okay, now this covariance matrix boils down to a diagonal matrix. Okay, all these cross terms become zero. Okay, so that's a further assumptions you can make. Okay. Right, so then the probability of x given ci, okay, equals to individual, right, individual features, individual, because now individual feature has no correlation with the other. So you can treat individual feature as its own Gaussian distribution, okay, now because they becomes a product, okay, of P of x, xj given ci and the product over j. Okay, we call this as a naive Bayes assumption. Okay, naive Bayes assumption. Then your discriminant function further reduces. Okay, so now becomes minus 1/2, right? Sum from j from 1 to d is the number of features you have. Each of the feature of each of the dimension minus that class's mean of that feature vector, of that particular jth feature's mean. Okay. Square divided by only the variances with respect to that feature. Okay, you don't care about the other feature anymore. Okay, because there's no correlation between them. There's no inverse you need to compute. You only have a division you need to do. Okay, there's no inverse anymore. Okay, it's because you don't have, there's no correlation between the two. Plus the log of P of Ci. Okay, if you look at this thing, right? Each of the x comes in for each of the ith class. It's going to give me a value. Okay, pick the one that's max. Okay, this is a distance function. Okay, essentially you're trying to classifying a sample based on a weighted Euclidean distance by measuring in terms of an SJ unit. Okay, to the nearest mean. Okay, so again, this particular formulation. Okay, when you're trying to say, okay, my x belong to ith class. You're going to pick the one that's the largest value, meaning pick the one that's the smallest distance, right, to the ith class. So if my sample weighted sum of my samples feature to the ith class is the smallest, it's going to give me the largest discriminant function, and I'm going to classify it to that. Okay, so I'm essentially implementing a weighted distance to the nearest mean, okay, as my classifier. Okay, and this will tell you, okay, this particular formulation, okay, there's a name behind this. It's called a naive Bayes classifier. Okay, again, if you want to implement naive Bayes classifier, very simple. Open up your MATLAB, open your Python, type naive Bayes, and you're done. Okay, and what is implementing? Is implementing this. It's basically making an assumption. You're doing a multivariate parametric classification using MLE as your estimation, and then assuming covariance matrix for each class is same. And also assume they're diagonal. Okay, once you make these 5 assumptions, it's naive Bayes classifier. Okay, 好，我这边再讲一下，这边一样，我们已经知道 common covariance。OK， 所以大家都长一样。OK， 我们可以再更进一步说，它不只长一样。OK， 它甚至没有，它甚至这个 feature 跟 feature 之间其实是 independent。OK， 它没有 cross correlation。OK， 所以我的 covariance matrix 本身会瞬间缩成一个 diagonal matrix， 那 diagonal matrix 其实就等同不用去处理那个 matrix， 它其实就变成各自处理各自的事情。OK， 所以因为我就跟别的 term 没有关系啦。OK， 我第一个 feature 跟第二个 feature 没关系，第一个 feature 跟第三个 feature 没关系，所以我在算这个几率的时候，我也不用考虑我第一个 feature 跟第二个 feature 之间关系，因为每个都 independent， 所以我的几率就最后把每一个 feature 自己的几率乘起来就结束了。OK， 那我的 covariance matrix 变成只剩下 cross term。没有 cross term， 只剩下 diagonal term， 你就只剩下这些 variances 而已。OK， 那 variance 怎么估？你就用 sample variance 去估它。OK， 所以这些 term 都消失之后，这个 matrix 就消失了，你也没有所谓的 inverse。OK， 好，那你的 discriminant function 的 form 就会被重写了。OK， ，OK， 变成一个 -1/2。J from 1 to D is indicate dimension of your feature，OK。第 J 个 dimension of T 个 sample， 对不对？我这笔是我要测试的资料，第 T 笔资料被拿进来测试，我去减掉 mean 嘛 of 这个 class， 第 I 个 class 这一个 feature 的 mean 应该是什么？除上这一个 feature， 它 overall 它应该要它的 variance 是什么 ？OK， 然后这个差值之后 take square，OK， 让它变成一个正数，对 ，OK， 然后加上prior distribution of log，OK， 那你把 x 带进每一个 discriminant function， 每一个 I 是代表每一个类别 ，OK， 挑一个最大的嘛 ，OK， 所以你可以去看这个逻辑变成，你可以去想为什么后面有这句话说，我每个 x 进入每个 I 挑一个最大 ，OK， 等于是我找一个最近的 ，OK， 如果我的 x 现在这笔测资离上某一笔 I 的 class，OK， 整体来讲它的命值在那边，我离它最近，我就说我是它，也很合理，很直观嘛 ，OK， 我这笔资料我想做分类 ，OK。那个类别有个 mean，OK， 这个类别有个 mean，OK， 我这笔资料我当然就找离我最近的是谁 ，OK， 我离他最近，我当然就最属于他 ，OK， 我离他最远，我就不是属于他，所以我找一群里面我离谁最近 ，OK， 那这个离他最近 Euclidean distance 再去除上每一个 feature 它本身它应该要有的变异度 ，OK， 那就变成现在这个 formulation，OK， 那这个naive Bayes这个 assumption 其实它就架构在这整个逻辑下，然后去假设 ，OK，covariance matrix 是个 diagonal matrix。那这 covariance 怎么样会是 diagonal matrix？ 你就是跟 feature 跟 feature 之间如果没有关联性，那它就叫 diagonal matrix。OK。Alright， 那如果图里 ，if you look at the plots，OK，everything is the same，right？This is x1， this is x2，right？This is C1 class, C2 class. They share the same covariance matrix, but now they are orthogonal。Right? Why? Because x1, x2 are independent. So your covariance matrix is it's only depends on sigma 1 and sigma 2. Okay, you can only model. You cannot model this become tilted. Okay, when it's tilted, that means your x1, x2 has relationship between them. Okay, only because they're orthogonal they become this thing. Okay， 好，这边再讲一下哈，一样，我们还是一样，假设大家都是同一个 covariance matrix， 所以两个类别都是一样，这是 x1 feature、x2 feature 嘛 ，OK。那最一开始的时候，大家可以自己长 ，OK， 我可以这样子写啊，我可以这样写 ，OK。好，再来就说，不行，两个长一样，所以两个某一种写方法要是一样的 ，OK。现在我把假设里面的 feature 跟 feature 之间没有关联性，所以它没办法再写了 ，OK， 它只能正正的，或者只能正正，因为它必须是 orthogonal，OK。因为我们 explicitly constrain 它 feature 1跟 feature 2之间要没有关联性 ，OK。如果它可以是斜的 ，OK， 表示有个 slope，OK， 表示这两个有个 correlation 嘛 ，OK， 所以它必然不可以有那个 correlation， 所以它的这个东西它就不会骂是斜的。所以你如果用 diagonal matrix、shear diagonal matrix 去 model，OK， 两个类别它的 data distribution 的话，你的假设是它只能这样正正的摆着，我的 covariance 只能这样正正摆，它不能再斜斜的摆的。OK， 你只要任何可以让它斜的，你就是必须不是一个 diagonal matrix， 你就要是一个 full rank 的 covariance matrix。OK， 那这个是很大的假设 ，OK， 但这个假设很好用 ，OK， 因为解了一大堆问题，对不对？但是这个假设适不适合 ，OK， 那也是见仁见智 ，OK， 但是这是一个很常用的假设。Okay, so this thing we call naive Bayes classifier. Okay, so if your xi's are independent of diagonal of the covariant matrix are 0, okay, your Mahalanobis distance that's being used in a Gaussian distribution is now become just weighted by 1 over sigma I. That I indicates the feature dimension of the Euclidean distance. Okay, so again, your P of x essentially is just this form. Essentially is this form. So of course you can make further assumptions. Okay, saying okay, every feature has the same variances. Okay, if you have every feature has the same variances, then this thing, the Mahalanobis distance again reduces essentially to Euclidean distance. Okay, so again you can find the nearest sample, okay, that class's mean, okay, as my class. Okay, that's without taking care of the variances. Okay, we call that the nearest mean classifier. Okay, so again, it's basically classifying based on Euclidean distance to the nearest mean. Okay, so if you have two classes, each class has a mean vector, another class has a mean vector. A sample that comes in, I just compute the Euclidean distance. If I'm close enough to you, then I'm you. Okay, I can also compare the Euclidean distance weighted by 1 over sigma I. That's naive Bayes discriminant. I can compute the full covariance matrix and then use the Mohanlava distance. Okay, that's a linear quadratic function. And if you say, okay, each of the classes has its own covariance matrix, I still compute the distance to you and then find the one that's closest. That's a quadratic discriminant function. Okay, again, depending on which SI you use, okay, you're implementing different function. Okay, and there are different names for this. Okay, in this thing, people call it nearest mean classifier, or they call it template matching. Okay. In this case, people call it naive Bayes classifier. Okay. In this case, people call it linear discriminant classifier. And this thing people call it linear quadratic discriminant classifier. But they are all the same. It's a play on SI. Okay, how do you make assumptions on SI? It gives you a different name of that classifier. 好，我们这边讲一下为什么要这样去讲。如果你去看 classifier， 在工具包里面怎么被列，它是每一个其实是不同的 classifier， 它有个自己的名字。OK， 但是它实物上逻辑是一样的。OK， 我们这边就举了大概3、4个 classifier 的名字。第一就 quadratic discriminant classifier， 再有 linear discriminant classifier， 再来有 naive Bayes classifier。naive Bayes classifier 应该是算是最热门因为它曾经一度是被拿来做那种 spam filter，OK，email 的 spam filter。你可以假设 ，OK， 你收到的每个字 ，OK， 每个字跟字之间 independent 是不是合理？不合理，但没有办法 ，OK， 这是先 independent， 然后你就说这是 spam， 这不是个 spam， 收了一大堆资料 ，OK， 然后就看 spam 里面有出现这个字的几率是多少，然后每个字出现几率多少把它乘起来 ，OK， 然后这边如果是不是 spam， 然后每个字出现几率多少就把它乘起来，看哪个比较大你就结束，那个就是所谓的 naive Bayes classifier。有好一阵子，大概可能10几20年前的 email 的 spam 的 filter 就是这样做 ，OK， 非常容易做 ，OK。那为什么要用 naive Bayes？OK， 很简单，你再往上走一层，它就太复杂 ，OK。因为就算是这个 SIS，OK， 它还是一个 full rank 的 covariance matrix，OK， 就算每个 class share 是一样的 covariance matrix， 它还是整组的，所以不用多，我们常用的字就2000个好了 ，OK，2000乘2000你就做不完这个事情了 ，OK， 所以它不太 work，OK， 但是他就做个假设，他说它就是 independent， 那 independent 这个假设合不合理？其实是不合理，每个字怎么可能是 independent？但他就是必须做这个假设，没有做这个假设，我其实也算不出东西来 ，OK。那它也不会很简单，就只做到 nearest mean，OK。nearest mean 或 template matching 是我完全不管那个 variance 那个项，我就是看这个类别的 mean 在这边，这个类别的 mean 在那边，我看我离哪个 mean 最近，我就说是它 ，OK。这感觉这个辨识能力好像有点太差 ，OK， 所以才会中间出现这个 naive Bayes classifier 这个逻辑 ，OK。那我等一下也会讲一下为什么 naive Bayes classifier 这个东西其实蛮好用的因为我们下一个章节会讲，今天应该有机会稍微提到 ，OK， 因为我们可以用一些 pre-processing 手法，让我的 feature 变得 independent，OK。我如果可以让我 feature 变得 independent， 我就可以很合理的用 naive Bayes classifier 来做这件事情，所以我就很容易把东西串在一起 ，OK。不过我们下一章节会教这件事情。但在这边想跟大家讲这些不同的 classifier，OK。Look at so diagonal， 如果说你 diagonal covariance matrix equal variances。Again, the covariance matrix now boils down to a spherical shape, right? Because your sigma 1 and sigma 2 they are the same. Okay, you no longer can stretch. Okay, it's just a circle, and they are orthogonal, and because it's only diagonal. So if you further make the assumption, become this. All right, so we've simply played with SI. Okay, this SI differences of SI gives you a different classifier you can implement. Okay, and then the real take-home message in this section is there's a trade-off. Okay, there's a trade-off in deciding what SI to be and how powerful you want your model to be. Okay. So again, if you have, we call them shared and hyperspherical. Okay, that means every class has the same covariance matrix. Okay, that covariance matrix is diagonal. Every feature has the same variances. Okay, in the end, you only have one parameter you need to estimate, okay? Because every class shares the same covariance. That covariance which is diagonal. Every feature has the same variances. In the end, you have one parameter you want to estimate, okay? Shared axis align, okay, meaning everybody shares the same covariance matrix that is diagonal. Off diagonal is 0. You need to estimate only D. Okay, they're shared, but they're hyperellipsoid. I mean, it actually does model the correlation between the features. Okay, all the classes has the same covariance matrix, but you don't make assumption that the off diagonals are 0. Okay, then you have D times D plus 1 divided by 2 number of features parameters you want to estimate. Okay, the most complex version, right? A different hyperellipsoid, so every class has its own full covariance matrix. Then you have K, indicate number of classes, D times D plus 1 divided by 2 of number of parameters you need to estimate, okay, from the data to be able to use in your discriminant function. And of course, all we know, you increase the complexity, meaning less restriction on S, bias decreases, variances increases. Okay, so basically, if you make the model more complex, on average, it's probably going to hit the right value better. Okay, but because you cannot collect enough data every time, so every time you have larger variances. Okay, so it's likely to create a suboptimal solutions. Okay, and you might want to also always assume simple models allow some biases to control for variances. We call those kind of process called regularization. Okay, 所以这边想讲的就是说 ，OK， 我们其实好像讲来只做一件事情嘛，对，我们还是做 parametric classification。假设 P of x given Ci 是Gaussian distribution， 假设它多维，然后这多维之后，我要 implement 那 classifier discriminant function， 我写出来了，发现 Si 很难搞 ，OK， 就把它 Si 开始做变形，变了4种样态 ，OK， 变了4个样态就出现4个 classifier，OK， 那这4个差异在哪边？只差在我需要估的参数量不一样。那参数量越大，就表示什么？表示我 model 越复杂，因为 model 越复杂，表示 on average 我可能会做得越准。但是你不可能一直收，除非你收到全世界的资料 ，OK？ 但是你没办法收，你每次只收固定量资料，所以你的 average 会准，但是你的 variance 会很高。所以你这一次做的实验，这一次去收的这些 data 进来，你可能给你是很有偏的，很偏的一个估计 ，OK？ 那你的 classifier 就会不准 ，OK？ 所以常常我们会说这是一个权衡的关系，你可能会希望。或许 model 不要这么复杂，但至少我每一次做这件事情，它跳动幅度不会太大，大概不会离那个距离太远，可以有一点点不准，但是不需要让自己 model 这么差这样子 ，OK？ 所以这4个你就可以在中间自己去选择。当然你 data 非常非常多 ，OK？ 你就可以对每一个做 SI，OK？ 那如果你 data 没有这么多，你最后才会做到这个作为 axis align 的这样。那这个是很常，就所谓naive Bayes classifier。像我们 span filter， 其实有一阵子最常变用就是这个。你可以想，这个字其实不难收，那 data 来讲已经算是很好收了，但他们当年还是用这个 ，OK？ 因为后面这2个实在是会让他们的 computation 太麻烦了 ，OK？ 第一个不好估，第二个那个 inverse 其实很难算 ，OK？ 这2个东西就会让整个 machine learning 演算法变得很痛苦这样子 ，OK？ Alright, just keep this in mind, OK? This multivariate method, OK? So again. Let's repeat this process. Okay, multivariate Gaussian distribution for parametric classification. Assuming this is real world, like we don't know this is the population. We don't know. Okay, assume this is the real thing. Okay, you go out collect the data, right? XX, circle. This is data you can actually collect. Okay, this is what's happening in real world. Okay, you don't know what happens, so you go out and collect data. You sample the world, give you some data. Okay, and it's your training data. If you assume each of the classes can be arbitrary, okay, arbitrary covariance matrix, then you have this thing, okay. Your discriminant function is quadratic, so you can have this kind of shape, right? Discriminant function is quadratic, so it's separating these 2 classes in a quadratic function, okay. When you make them as shared covariance, okay, so that means these 2 they have to be the same, okay. Okay, so now they start to look a little like this. Okay, so it'll shift this over here, this will shift over here, and then they become the same. Okay. Now further you assume, okay, what if they are diagonal matrix? Okay, then this tilted cannot happen. It has to be sort of orthogonal. Okay. Now it becomes this shape of your covariance matrix. Okay. Finally, you can say, okay, maybe the x1, x2 axis, okay, they are not they are the same. Then this becomes a spherical circle. Okay, it becomes this. Okay. So if you don't know this, okay, which one is the best? At some point, it's hard to tell, right? Everyone looks okay, right? So, and that's the issue. Okay, if you know this, of course you know this is better. If you don't know this, all you do is collect all this data and start fitting these circles on this thing. Okay, with your eyes, it's very hard to tell. Okay, which one actually looks better. Okay, so at that point, it's an engineering trade-off. Okay, you want to take this as your diagonal measure, so we can implement naive classifier. Or you say, okay, I think this is better. Okay, because give me a quadratic discriminant classifier that I can use to classify between the two. Or maybe you say, okay, hey, this maybe as simple as this. Maybe these are just outliers. Okay, maybe these are noise that you collect. Okay, maybe this is good enough. Then it becomes we call the template matching nearest mean classifier. 好，这边也再讲一下这中间这个逻辑哈。这个假设这真实世界就长得是这样，所以你在做辨识的时候，其实最佳辨识条是这边，这是真的 data 本身的分布。OK， 全世界针对这件事情，针对 x1、x2， 针对这个类别，针对这个类别，它 data 分布长这样。OK。那这个是我们不知道的嘛？我只是想要做这两个东西的分类 ，OK， 所以我只好去收 data，OK， 所以收 data 我就等于在这上面去取样嘛 ，OK， 所以取的这些x 跟取的这些圈是另外一个类别 ，OK， 红色的。那就像刚才讲，我们在做 parametric classification， 我其实就是在找一条 OK，discriminant function 去拆两个类别。那怎么拆呢？我可以假设它这个别的类别是高选，那如果是个别类别高选，它的 SI 是各自都有了，那它就会长这样，它就长这样。我中间可以做 quadratic discriminant function， 因为它是 quadratic， 所以它可以有个 square 的样子，它可以有个这样子曲线的感觉。OK， 我可以说它们两个是要一样的。OK， 所以一样嘛。那既然是一样，就会是两个加起来乘上各自的权重，所以各自就会被位移往中间位移，对不对？它就变长这样，再长这样子。OK， 那你可以说，我不想要做 shear covariance 的 full covariance， 它或许它就只是个diagonal measure， 你就把它调正 ，OK， 把它调正 ，OK。那 data 都是这些哦，data 都没有变 ，OK， 只是你拿什么东西去 fit 它而已。OK， 这个 assumption 是你们 make 的 ，OK。最后来说，其实或许 x1、x2 这两个它不是个椭圆形啊，其实是个圆形 ，OK， 因为它的 covariance 是一样的 ，OK， 它的 variance 是每一个 feature 是一样，它就变个圆形，它变个圆形 ，OK， 你还是可以 fit，OK。还是会给你一个 discriminant function 长在那边，这边还是一个 discriminant function 长在那边，那 discriminant function 这边也是 discriminant function 长在这边 ，OK， 这是你想要做的事，但你不知道，这是你收的 data， 那你要决定你要用的是这个还是这个 ，OK， 那决定的原因是什么？因为这四个东西给你的模型的能力不一样，但它所需要的参数估计也不一样，它所要运算的资源也不一样，哪一个比较好 ？Trial and error，OK， 所以要做实验来做一些 cross validation， 你要有个 train development，OK，test 这样的一个 split 来去最后试看看 ，OK， 哪一种东西会是最佳，或者说至少在当下是最好的一个选择 ，OK。就 just keep in mind, right? So this is when you decide a particular classifier to use or assumptions to make, okay. Plot it, look at it, and then maybe try it and see which one works out the best. Just know the pros and cons when you choose a particular classifier. Okay, there's no single classifier that works the best for everything. Okay, there's only good and bad. Okay, there's good thing about this. There's a bad thing about this. Okay, choose based on your current condition of application. That's the key. Okay, all right, move on to the next section, dimensionality reduction. Okay. What's dimensionality reduction, or why reduce dimensionality, right? Dimensionality means the number of features you have, okay, for each of the sample, okay? You want to reduce that, okay? Why you want to reduce it? First, of course, reduce computation, okay? If I have 10,000 features, if I only need 100, okay, it makes my computation really fast, okay? So it's reducing the time complexity, okay? Reducing the space complexity, okay? Again, if you have 10,000 features, I can find a way to select or retain only 100 features. Only need to record those values. Okay, so you can save memory. Okay, save we call space complexity. Okay, save the cost of observing features. Okay, every time you go out and measure stuff. Okay, every feature you measure, it's a process. Right, it takes time. Right, even if you ask people to fill up a Google form, right? Every extra question, extra time, right? So the number of features to collect, if there are fewer, then the cost of collecting data will be much less. Okay. Also, simpler models are more robust. Simpler models meaning less input, meaning less features. Okay, and less parameters. Okay, and less parameters makes the model simpler. Also, simpler model is less variable. Okay, so let's also make it also better. Sometimes they're more interpretable, and also a lot of times when your features are over 3 or 4 dimensions, you cannot see with your eyes anymore. Okay, you can use dimensionality reduction methodology to reduce it to, say, 2 dimension or 3 dimension. You can actually see the data. Okay, so with your eyes. So there are many ways that we can do this. 所以我稍微讲一下，我们从 multivariate 很快的再继续往下延伸了。我们先从我们怎么做辨识 discrete function 是什么 ？OK， 这个背后是用统计几率模型哪一个做？做完之后 ，OK， 我开始从 feature 角度开始想事情。OK，feature 一个不够，多个。OK， 那多个就把这个 discrete function 把它放大。OK， 放大之后有 SI 问题，我就形成了一系列的 classifier 可以做。现在再回头说，那我 feature 放大我们越放大好像越好，但是放大到一定程度好像太多，我可不可以收一堆再把它减少 ？OK， 就开始做所谓的 dimensionality reduction。OK， 因为有可能一开始收了10000个 feature、1000个 feature、1500个 feature 都可以，可能太多。OK， 那我有没有什么数学的手法让这些 feature 变得少一点 ？OK， 那少一点有很多好处，因为你想想我们前面的计算 ，OK， 其实都是你 feature 维度多少个，就会影响了后面那个 covariance 那些数量有多少个，参数量有多少个。那你的参数量越少，我记录资料就越少，我要运算的速度就会越快。OK， 所以有没有比较数学的方法 ？OK， 一个 systematic 方法，而不是我就是一开始只收3个。OK， 你收3个，如果你挑到错的3个就很麻烦。我先收了一大堆，可不可以看我在很多的里面去挑出几个是有用的，或是减少变成几个维度是有用的 ？OK， 这种叫做 dimensional reduction。那它这边讲就它很多好处啊。OK， 所以比较计算比较快。OK， 储存量比较少。那也有个东西比较重要，就是说，当你 feature 维度很大的时候 ，OK， 其实你是没办法看的。OK， 就是4、5维以后，就不然我们就看到2、3维而已嘛。所以如果你有一些手法让它变为2、3维，你就可以用画的，可以真用眼睛看一下我的 feature 长什么样子。OK， 这也是另外一个好处啊。OK，so there are 2 types of feature or dimensionality reduction approaches. One we call the feature selection. OK，out of the feature you choose or you extract. OK，pick a subset. OK，that make it best work for you. OK，another we call the projection or extraction approach. OK，meaning imagine in a feature original sits in a d-dimensional space. OK，let's try to find a projection matrix project into a lower dimension. OK，how do we find that projection matrix, right? From a d-dimensional to k-dimensional, where k is much smaller than d. OK，that's we call a projection or extraction procedure. OK， 好，这边讲一下，整体来讲，我们会大概带一些这种 feature selection 或 extraction 的机，但它整个 dimension reduction 大概就可以想成大概2类哦。一个是我的原本就在算那些 feature、savings 啊、income 啊等等这些，我可能算了1000个，我想要从里面挑出几个是有用的。OK， 但我不去改变它，我只把它挑出几个是有用的。OK， 另外一种是 extraction 或 projection 的方法。OK， 我可以说 OK， 我的 feature 不是说挑几个有用，而是说这些 feature 之间我可能可以把它浓缩一下。OK， 它原本是在低维度的空间 ，OK， 这是比较线性统计的概念嘛，低维度的空间，其实它可能可以透过 k 维度来去表达它，其实也表达得非常好 ，OK， 所以只要 k 比 d 小，那我其实 feature 数量就变少 ，OK， 所以这是另外一种比较 extraction 或 projection 的方法，去把我的维度下降，这在里面我就不会把 feature 丢掉，我会把 feature 跟 feature 之间关联性试图浓缩之后，变成一个比较低维度的东西。那在第一种 selection 的方法，它其实是把 feature 丢掉 ，OK， 我就是挑几个我觉得有用的东西把它留下来 ，OK。那这2个方法都 effectively 可以让它变成一个比较低维度 ，OK， 少一点 feature 的一个过程 ，Alright。So feature selection, right? Choose k less than d, ignoring the rest of d minus k feature, right? So you can throw away some of the features. Okay, how do you select? Okay, that's a feature selection approach. There are tons of subset selection algorithm. Okay, so you can imagine, right? Basically, if you have set of features, okay, how many subset you can generate from the set of k or d features? Okay, how many D sets of subsets can be generated from, let me get the terminology right. How many K subset can be generated from a D set? Okay, so it's like a D choose K type of thing, right? So how do we best use some methodology to select those K subset? Okay. Again, this is hard. Okay, we'll tell you a simple way of doing things, but if you want to do it in a maximally correct method, okay, it's very difficult. Okay, and this is an issue of combinatorics. Okay, there are too many combinations. Okay, that you can choose. Okay, and then there's no way you can go through each of the combination. There are too many of them. Okay, so there's some simplification, simple way of doing things. But usually they're not globally maximized. Okay, but there's one set of approaches. Again, the other set is called feature extraction or projection. Project the original xi, okay, I from 1 to d dimension to a new k, which is less than d dimension of zj, okay, j from 1 to k. So original is xi, okay. In the end, what you have is zj, okay, where j go from 1 to k. So j, this variable has only d dimension. Original features you have, z variables has k dimension. Original features x has d dimension. So find a projection matrix to that. Okay, in a feature selection, this kind of subset selection kind of stuff. Okay, it's difficult. Okay, imagine if you have d-dimensional feature originally. Okay, there are essentially 2D subsets of d features. Okay, how do you exhaustively search through all of them to give you which set is the best? Okay, this is not possible. It's too many. Okay, 1,000, 2 to the 1,000 power. Okay, it's not a set we can actually enumerate through our computer and do things. Okay, so it's not possible to look at every subset that's possible from the D sets of features to look at, okay, this one is better than the other one. Okay, so exhaustive search is usually impossible. Hence, there are some simplified ways of doing search. Okay, one is called forward, one is called backward. Forward is simple. Okay, so basically you start with one feature at a time. Okay, so again, you start with the set of feature. There's nothing in there. At first iteration, okay, you put every feature in one at a time. Okay, and with some error function. Okay, or some measurement of how well that feature behaves. Okay, find the one that's performed the best, or find the one that gives you the minimum error. Okay, keep that feature. Okay, now going through the second iteration. Okay, the second iteration will say, okay, I'm going to take the best first round feature, combine with each individual feature again, and look at which combination give me the best 2 feature subset. Okay, keep that second feature, and then move forward again. Okay, and look at this 2 feature in combination of one of the other features. Put it in, give me the smallest error. Once that's done, okay. Then you have the 3 subset feature. When do you stop? You stop when this error is no longer decreasing. Okay, then you finish selecting. Okay, you finish selecting. Okay, it's called forward selection. Okay, backward selection, very intuitive. Do it backwards. Okay, you start with the full set of feature. You remove one at a time. Okay, the one that's being removed give you the smallest error. Okay, then remove that one. Okay, now the next round keep removing. Okay. When do you stop? You stop it when you remove one additional feature and it no longer decreases the error, and then you stop. Okay. All right, that's forward and backward. Okay. These two are greedy, not globally maximum. Okay, because you never, every time it's the best. It doesn't mean looking at the whole set is the best. It's only one for that particular step is the best. Okay, right? So there's a modification that's in combining forward and backward. I call it floating search. Okay, they would add K features forwardly, okay, and then remove L feature, okay, where K is L. So forward K, backward L. Okay, forward K, backward L. Forward K, backward L. Okay, so in that way, it can actually, find a little bit better set than this forward and backward. Okay, 好。我来讲一下啊，这边没什么数学，它其实就是往前走、往后走。OK， 那我如果第一个 feature，OK， 我总共有2D 这种 subset 可以找，而我每个 set 我都去跑看看实验，说哪一个比较好，用我的 train 跟 validation， 对 validation 可以让我测 ，OK， 第一种 set 还是第二个 set 还是第三个 set 会比较好 ，OK， 那你跑不完太多了 ，OK， 所以就有这两种非常简化的方式去做这件事情 ，OK， 我可以一开始叫做 forward search。forward 就是一次走一步 ，OK， 一次把一个最好拿进来 ，OK。所以，假如说我100个 feature， 哦，每一个 feature 在第一步的时候就每一个都跑一次 ，training，OK， 测试，哦，看看结果是多少。第二个 feature training 测试，一个一个 feature 跑。第三个 training 测试 ，training 测试，跑完100个，你就有100个 error， 找哪一个 feature 给你最少 error 留下，然后第5个 feature 最少 error 就留着 ，OK。那留着的时候再开始找下一步 ，OK， 那就5再配上1，那5配1 training。再看它测试，5配2 training 测试，5配3 training 测试，5配4，一直配到5配100 ，OK， 看看哪个给你的 error 最小，留那个。假如说5跟6是最小啊，留下来5跟6 ，OK。再来再走一步 ，OK， 5、6配1， 5、6配2， 5、6配3， 5、6配4 ，OK， 5、6配到100 ，OK。好，一直到什么时间你就不再做这件事，一直到我下一次这个 error 没办法再比上一次再更小了，我就停了。那我可能最后选就是5、6跟100，OK， 这3个 feature 可能是最好的。要 forward search，OK， 那剩下的 feature 你就丢掉了，啊，你就不用了，因为我挑了100个，因为我挑了3个我觉得最重要的 feature， 哦，那最重要怎么 define？ 你的 define 的方法是用一个我的 classifier 去 train，OK， 那这可以是刚刚那个 linear、quadratic 随便，看你要用哪一个都可以 ，OK， 就哪一个你选定的那个，然后做个 validation， 全部做完之后，确定了那3个 feature 之后，你用那3个 feature 去做个 training， 再去做一个真的 blind test，OK。好 ，backward 基本上一模一样的概念，但是就反过来做 ，OK， 反过来做。那 backward 它其实是一次丢一个，全部 feature 一开始都用，我是丢一个 ，OK， 1到100，我是算去那个100维的 classifier， 然后现在 OK 我就丢个变99了 ，OK， 丢第二个也是99，那看看丢掉哪一个让我的这个 error 会比较小 ，OK， 那我就选那个 ，OK， 那再丢到我的 error 不会再更小了，那我就会停了。OK， 好，那就会有 forward 跟 backward。forward 跟 backward 你可以想象它就有几个 intuitive 的，我们不会去证明它，但你 intuitive 就可以去想，它其实个别有些坏处。OK，forward 就是它找不够多，它就停了。OK， 因为我是一步找一个，一步找一个，我就找不够多，我可能就停了。OK， 那 backward 可能是我丢不够多我就停了。OK， 因为有些其实根本没有用，我只是还被我挑到它没有用。OK， 那或者说我还不够，或是它配它才没用，它被丢掉。OK， 所以就是我会留太多，有可能它跟它凑在一起是有用，那其实会没用啊，这个东西其实可以丢掉了。OK， 所以这样子的一个东西它会找不到。这个是 forward， 是我有些可能是这两种配对，不是因为现在最好，而是未来这样子配起来还会比较好。那个你会找不到。OK， 所以这两种都会特别会让有一些东西找不到或丢不掉。OK。因为它并不是 global， 你并没有勾述所有 due to the D subset 去找它 ，OK， 所以你找不完这么多 ，OK， 所以当然就会有一些简单的一些方法去 fix 啊 ，OK， 例如说你就 add K feature， 然后 remove L 个 feature，OK， 你一次做 K 步的 forward， 再做 L 步的 backward， 再做 K 步的 forward，L 步的 backward，OK， 那这样子的一个 feature selection，OK，usually they're good，OK，but they tend to be time consuming. Because every time you do one at a time. This is time consuming, this is time consuming, this is even more time consuming, okay, because you do K and you remove L, and you do it again and remove L, okay, so that's a lot of bookkeeping and then computation. But usually it gives you an improvement in terms of classification, in terms of accuracy. It will also give you a small set of features to retain, okay. Good thing is that, it tends to really help you improve, the performance improves. Okay, bad thing takes a long time, and also bad thing is once you fix on those features, the rest of the features are being thrown away. Okay, so basically you say, okay, those are no longer useful. I'm gonna throw them away. Okay, so that's the thing. Okay. All right, here's just a visualization. Say you have 4 features. Okay, right, each one you run, the different shapes, meaning different classes. Okay, this is one feature, second feature, third feature, fourth feature. You should look at them and which one gives you the most discriminant between the 3 different shapes of the classes. This one, right? So all the pluses are here, all the crosses are here, all the circles are here. So this is a good feature. Okay, pick that one as the first part. Okay. Now that F4 is the best one. That combined with F1. F4 combined with F2, okay. F4 combined with F3, okay. and look at your features and then say, okay, which one give you the most, separability? Okay, from the eyes, okay, it seems like this one is good. Okay, so can tell. 但这边你会想说，哎，好像有些看起来还不错，对。但其实这种这种 searching 的 algorithm 它的问题是它跟你选的那个 classifier 有关系啊，因为你会 take 某一个 classifier 做 training 去看在那个 classifier 状态之下，它的准度是多少。所以我换一个 classifier，你可能选到的 feature 就不一样。换一个 classifier，你选到一个 feature 可能就不一样。OK， 所以它是我们 this kind of method we call a wrapper method. Okay, it wraps around the classifier. Okay, whatever the classifier think this is the best feature, that is the best feature. Okay, it doesn't care the actual thing, right? So if you change a classifier, it's going to give you a different set of feature. Okay, just to keep that in mind. Okay. I want moving quickly to do again. That's the feature projection approach. Okay. Last thing I want to talk about here. Okay. These are very simple feature selection approaches. If you're interested in knowing more about feature selection, okay, there are tons of methods. Okay, usually it boils down to two parts. One is how do you design this error function? Okay, how do you say this feature is good? Okay, do you want to wrap around classifier or do you don't want to wrap around classifier? Okay, there are two options you can think about doing this. There are selection mechanisms that don't want to wrap around classifier. Let's just directly compute something between the features and the label. Okay, that's one kind of extension. A more complex, right, is basically a kind of a combinatoric searching problem. Okay, if there's so many subsets, okay, of course I cannot go through all of them, but I don't want to just go through one at a time. Okay, is there some search algorithm that makes this seem more efficient? Okay, that's there's some math I can design to actually speed up that whole searching process. Okay, that's again another set of feature selection approaches. People are trying to develop. Okay, so these are just simple approaches. Okay, 我稍微讲一下，因为我不想 undermine 就是 feature selection 好像没用，它其实很有用。OK， 它其实最后选出来也会有效，但它也不只有这几个方法而已，这是最基础的方法。它在如果大家对这种方法有兴趣，它在往下延伸的时候，大概你看它基本上几个延伸的方法。第一个就是它会去选择我怎么去决定这个 feature 是有用的。OK， 现在的决定法是我绑着一个 classifier， 它跟我讲，如果我用这个 feature 配这个 classifier， 给我的准确率是最高的，或者错误率最低的，我就把它拿来用。OK， 我就把它组合出来。但有些不是这种 wrapper 的 ，OK， 我其实就直接算这个 feature 跟这个 label 的某一些数字 ，OK， 算出来如果比较高，就是它的关联性比较高，我就用它 ，OK， 这也是另外一种方法 ，OK。还有做一些组合的，一次加一个，或者一次加多个 remove 掉，一次加多个 remove 掉一个。你也可以一次不加一个，你也可以是加两个，一次加三个，你可以一次用3个去算，也可以是用4个去算 ，OK。这个道理是什么？这后来就变成其实是在 set 是 combinatorics。我一些排列组合，我总要把这个排列组合最有效的把它组出来 ，OK。然后哪些东西排列组合要先被跑，哪些排列组合不用先被跑 ，OK。那么有一些这个 optimization 的手法可以做这件事情 ，OK。那又是另外一种套路来做 feature selection。不过这整个系列都在做一件事情，我有一组 feature，OK， 我要从里面挑一些 subset 符合某一些标准，然后留下来，剩下丢掉 ，OK。这样子的 dimensional reduction 是 for the feature selection，OK。然后后面延伸也是有很多的。那 feature selection 有一个好处啦 ，OK， 这边有一点时间我讲一下。One of the good thing about feature selection is the feature you maintain. Usually they're more interpretable. Okay, so if you look at, if you like problem set up in biology, okay, medicine, okay, gene selection, okay, which gene helps me predict the diagnosis, okay. Well, a lot of time they're doing feature selection. Okay, they're doing selection out of the tens of thousands of features, tens of thousands of genes. Which one help me do prediction whether you have a particular cancer risk? Okay, because they need to know exactly which gene. Okay, they cannot just massage it and becomes a new feature. Okay, and then you cannot explain that new feature. So, feature selection has ability to maintain the original features interpretability. Okay, so that's also another good thing about feature selection. Okay. Alright, feature projection. Okay, I want to talk about one simple feature projection approaches. I'll start, and I don't think I'll have time to finish. I'll talk about it more on Wednesday. Okay. principal component analysis. Okay. So basically, the projection approaches says, right, your original feature resides in D dimension. Okay. We want to form another lower dimensional space and then take the feature's original in the D dimension to that new feature space. Okay. Through some optimization approaches. Okay. So basically, you find a lower dimensional space such that when X is projected to that space, some information loss is minimized. Okay, because your projection to a lower dimensional space, that means you're using fewer number of dimension to represent original feature. There's something has to be lost. Okay, you want to find things that lost at the minimum. Okay, when you do that projection. Okay, so we can define some terms to say, okay, when I do that projection from D to K, some information loss is minimized. Okay. So we know the projections of X onto the directions of W, is W transpose X, right? This is, again, linear algebra, okay? Again, not machine learning, okay? It's all linear algebra math, okay? W transpose X give you a new dimension Z, okay? We want to do something. We want to say, okay, find a transpose or projection matrix or projection vectors such that the variance is maximized. And we call this variances of Z. Okay, it's called information. Okay, so the variances in that new space Z is maximized. Okay, when you project original feature in X, right? There's a variance of X, and then you project to a lower dimension. Okay, through this projection, I want to make sure after I project over there, the variances is kept at maximum. Okay, here we call the variances as the information as Z. Okay, so let's see. Variance of Z is variances of W transpose X, right? And then variance, just write out the actual math. Okay, expected value of W transpose X minus W transpose mu to the square. Okay, now that quadratic term is expanded, expected value of W transpose X minus W transpose mu and W transpose X minus W transpose mu. Expected value of W transpose X minus mu transpose W. Okay. Only X is a random variable. W take it out. Okay, these two are just constant terms. W transpose expected value of X minus mu transpose W, and W transpose sigma W. Okay, so sigma is what? It's the variances of X. Okay, so we want to find we know the variances of Z, okay, equals to W transpose the variances of X and W. Okay, we want to find W such that when I do this projection, this variance term is maximized. OK， 好，这边我们讲一下，后面就解了，所以没什么问题啊。但我想说 ，principal component analysis 其实在做一件事情。那 projection 其实所有 projection based 的dimension reduction 都在做同一件事情，就是我找一个 projection 的 matrix，OK， 或者 projection 的 vector。我把我的 feature 往那方向 project 过去之后，我要把什么东西留下来 ，OK？ 因为它一定 project 到比较 lower dimension，OK？ 我 project 过去之后，我希望它达到的目标是什么？我可以透过一些设计 ，OK？ 数学上的设计，让我 project 过去之后，我的东西可能不会掉太多 ，OK？ 我什么样的资讯会被 maintain，OK？ 那这边我们讲的就是它的 variance 是我们用 variance 来代表一个 feature 本来有的一些资讯量 ，OK？ 那这边有点抽象哦，以后大家有机会去学消息理论等等之类的，就会知道说，其实 variance 是一个很重要的概念 ，OK？ 一个东西它要有变化量 ，OK？ 它才带有资讯量 ，OK？ 一个东西不会变你就没有带有资讯，合理上是这样嘛，对，你这个东西不会变，那其实你等同你没有带，就是因为你会变，所以才代表你这个东西很带了一些重要的资讯，所以你才会变 ，OK？ 你都不会变，你就是个固定的人，固定的事情，固定的东西，那些固定的东西就不带有任何的资讯 ，OK？ 所以这个概念上，我们其实 PCA 也是引用了这样的一个概念 ，OK？ 我希望 variance 在被我做这个 projection 的过程中，因为它势必被我丢掉的东西，我希望丢的过程，或者说被我在转移的过程，我会去转到一个它 variance 最大的位置 ，OK？variance 最大的位置。那后面我会讲，它在转的过程，我们希望它转的时候 ，OK？ 我找到的那个空间，它的每一个新的 feature Z 这个空间，它每一个维度之间是 uncorrelated，OK？ 这也是它另外一个特性 ，OK？ 希望我每一个 dimension 之间是 orthogonal，OK？ 所以我可以去 project 到一个新的象限里面，但是那个象限里面它是 orthogonal，OK？ All right, so again, we just find omega such that its variance is maximized, okay? So we want to maximize, say, Z1, okay, the first dimension we want to do, okay, subject to, that projection doesn't add anything to it, right? Subject to the norm of that projection vector equals to 1, okay? So essentially you're solving this equation, okay? You want to maximize the variance, right? W1 transpose, right? A projection vector times, the covariance, okay, and W1, so this is the variance as it projected onto W1, right? As it projected onto Z1, okay? Subject to a constraint, W1 transpose W1 has to be norm equals to 1, right? So basically this term minus 1. Put a Lagrange in the front, okay? So this is a Lagrange multiplier constraint solution, okay? You've learned that in calculus, okay? I'm pretty sure most of you forget, okay? But recall that, okay? It's you use this Lagrange to solve like boundary issues, solve for a multiple constraint, right? So you have a constraint. This thing is to be maximized, but under the constraints of W1 and W1 norm has to be equals to 1. Okay, so you add a Lagrange multiplier, and you say you d this thing and solve set equal to 0, and then you eventually you'll have this form. Okay, once you solve this Lagrange multiplier problem, so you have this form. Okay, the covariance of the x multiplied by the first projection vector, okay, equals to alpha W1. Okay, if you look at this term, okay, a matrix times a vector equals a constant times a vector. What's this? Right, a matrix times a vector equals a constant times a vector. This means these vectors are eigenvector of this matrix. Again, this is linear algebra, okay, again, nothing new, okay, so in the end, what you're trying to do, right, you're trying to find W1 is an eigenvectors of this thing, okay. You want to find the one that has the largest eigenvalue, find the one that has the largest eigenvalue for the variance of Z1 to be maximum. Okay, so basically, through this approach, what you're trying to solve is taking a covariance matrix of your data, okay, find eigenvalue decomposition, okay, and then find the first eigenvector that corresponds to the largest eigenvalue. Okay, once you've done that, okay, it gives you the first projection matrix. 好，我们再讲一下，这边一样哈。Machine learning 本身没有新的数学啊，我觉得它的麻烦就是它把很多科的数学统统拿起来凑在用那样子。OK， 稍微复杂一点在这边。OK， 但是它其实本身没有新的数学。你看，我们几率啊、统计啊，都是一样的东西。这边线性代数啊，其实是一样的东西，都大家都学过，曾经某一年学过。OK， 某个年度、某个时间点都可能学过。那只是这个凑在一起的数学变比较复杂，但实物上它就是把它凑在一起用。我们训练就是把这些数学凑在一起用。OK， 好，所以我们让 variance of z 被 maintain。OK， 那我们就要解出来，就是我们知道 variance of z 就等于variance of z 等于这个 projection matrix 这个 w。OK， 那我现在一个一个找，我先找出第一个 projection 的方向。OK， 因为我要把原本的第一维降到这个比较少的 k 维。OK， 先找第一维应该往哪个方向走？那第一维我要 project 它就是 W1 嘛，所以我的 W1 去乘上这个 covariance matrix，OK， 乘上 W1，OK， 那我要 maximize 它 ，OK， 但你如果只是纯粹 maximize 这个，那我的 W 设很大就好了嘛，所以你不可能让 W 就设很大，所以你有个 constraint， 我这个 norm 应该要是1，OK， 因为就不会再加大它的值 ，OK， 所以你本来就我想让这个最大，但是它一定要在一个特定条件之下最大，不然我就这个是一个这个 trivial solution， 我 W1 就让它一直变很大，那它不是一个 unit norm 的 vector， 它自然就很大，所以我 constraint 它一定要那个，你把它写起来就是 Lagrange 的问题，而 Lagrange 问题你去解它，解完 Lagrange 它会出现这个公式 ，OK，a covariance matrix 乘上 W1 这个 vector 等于 alpha W1，OK， 再细看这个其实就是一个 eigenvalue decomposition 的问题，因为一个 matrix 乘上一个 vector 等同一个 constant 乘上一个 vector， 表示这个 vector 是这个 matrix 的 eigenvector，OK， 那所有问题就变成在解这个 matrix 的 eigenvector 的问题 ，OK， 所以我 PCA 其实在解 covariance matrix of x 的 eigenvector， 然后我的每一个象限最大的 variance 就是第一个就是最大的 eigenvalue， 第二个就是第二大 eigenvalue，OK，continue。So the second principal component, right, same thing, maximize C2, the second dimension, okay, we still constrain, okay, W2 that has to be equal to 1, and we also constrain it has to be orthogonal to W1. So maximize the variances minus this has to be 1, okay, also constrain that your W2 and W1 has to be orthogonal. Okay, so basically doubly constrained. Okay, again, but eigenvector, they are originally, of course, they're already orthogonal to each other. So you're still finding essentially the eigenvector of this covariance matrix. So you're still solving this equation. So you have W2 is just another eigenvector of the covariance matrix of X with the second largest, so on and so forth, and continue. Okay. We know sigma is a symmetric matrix. We know two eigenvectors orthogonal. Okay, sigma is a positive definite matrix. Okay, so all eigenvalues are positive. Okay, again, sigma, if it is a singular, then it has a lower rank. That means the dimensionality required is k is probably less than d. Okay. All right. So again, these are some matrix properties that people probably forget, but you should know. Okay, so again, but PCA is a projection approach. Once you're done, you find all these W matrix, W1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to, say, K. Okay, then you can project the original feature into the new Z1 to ZK. Okay, and by doing that, you make sure, okay, the largest variances are kept at every projection. Okay, by doing these kind of approaches. Let's do a visual plot. I think this hopefully tells something. Okay. Your feature original x1, x2. Okay. If you look at the covariance matrix and their distribution, say looking like this. Okay. So Z is some W transpose X minus mean. Okay. So where the columns of W's are eigenvectors of sigma, M is just a sample mean. Okay. So what the PCA really does is they look at the distribution here. First, they subtract the mean and say I'm gonna move some mean. So I'm generating a new axis Z1 and Z2, where the 0 is located at the mean, because I subtract the mean now. So my 0 point, the original point now is 0, 0 here. Okay. I'm gonna find an axis. First axis that has the largest variances. Okay, along this circle, what's the variance the axis that has the largest variance is here, right? Okay, the second largest here. Okay, and also these two has to be orthogonal. Okay, so what you're taking is saying originally my viewpoint of my feature is x1 and x2. By eigenvalue decomposition of covariance of x, okay, I find a projection matrix W. Okay, that I can project x through these eigenvectors after subtracting the mean. So my x1 and x2 now become z1 and z2, where they have 0 mean. Z1 and z2 are orthogonal. Okay, and we are also sure z1 is on the largest variances of the original feature dimension. Okay, 好，我这边讲一下，所以 PCA 到底在做什么？如果大家可以想一下，我们做一个线性的 projection matrix， 它可以做的什么？它就是可以位移 stretch。哦，对，实物上就这样，这个一个线性的 linear algebra 的一个投影，它可以让原本 data 可以做到的事情，就只有位移跟 stretch， 两边拉、位移、移动。OK， 就只有这些动作可以做，对不对？所以 PCA 其实它就在做这些动作，只是它做的时候它有个道理在，它在做什么道理？它在说我要把我的象限位移到一个新的位置 ，OK， 那个位置是什么？那个位置是中心点00，是原本 feature 的 mean 的位置 ，OK。再来，它做了一个旋转位移，让我的这个 axis 会跟我原本 covariance x， 就是它的 data distribution 最大的那个方位的 variance 去 align，OK。第二个 axis 会跟第二大的 variance 的方位去 align， 这两个它要 orthogonal，OK。所以我原本在量是量 x1 跟 x2，OK。我看了 x1 跟 x2， 它之间有一些关联性。OK， 我算了它这 covariance matrix， 我去解它 eigenvectors，OK， 解完之后我就可以拿着 x1、x2 去投影，透过这些 eigenvector 投影完之后，我就会到一个新的 feature，OK， 那个新的 feature 你可以想象它其实就是一个 z1 跟 z2 的 feature， 就是一个新的 space， 新的空间。这个空间怎么样呢？这个空间其实它就是00在这边 ，OK， 它的 z1 就跟原本的 x1、x2 它的 covariance 最大的第一个维度在这边，第二个维度在这边 ，OK， 所以 PCA 在做的事情就是把 你可以想象它在做一个视角的转移吧。OK， 这样想。OK，it's a viewpoint change. OK，you originally start with x1, x2. Find a way to rotate your axis. Right? You take this x1, x2 axis, rotate based on the data property. Okay, the data property is here's the largest variance of x. Okay, here's the second largest variance of x. And if you have multiple, then you have multiple. You rotate, shift it here, and that becomes a new axis for your features, a new viewpoint in your feature. Okay, so you lost the original x1, x2. All you have now is z1 and z2, and these features become the input to whatever you want to do later on. Okay, that's PCA. And you may ask, okay, through this approach, right? So once you can continue to do finding the eigenvectors, when do you stop? Okay, when do you stop? Okay, you can do this thing. Okay, you can compute this proportion of the variance explained. Okay, so total lambda 1 to lambda d, right? This is the you solve that full rank. Okay, every vector has a eigenvalue, sum of all the eigenvalues. Every time you pick the largest one, okay, second largest one, third one, up to the kth largest one, okay. So the ratio between the two, okay, if it's hit enough points, say 90%, 95%, 99%, then you can stop, okay. Then when you stop, okay, then you have a much fewer dimension than the original D. Typically, we set POV greater than 0.9. Okay, we only throw away 10% of the original variances in the data. Okay, so usually you have things like this. Okay, number of eigenvectors and then the eigenvalues. Okay, and then this is the proportion of variances explained. Okay, you see around 20 vectors is probably about 0.9. Okay, so originally you have 60 something features. Now you only need 20. Okay. And then you take these 20 eigenvectors as your projection matrix, project the 60-dimensional features into the 20-dimensional feature. OK， 好，我这边再讲一下，好，这边是如何去选这个 K 个K 个，因为我要做dimensional reduction 嘛，就会做 K 个这个 feature， 剩下 K 个 feature 怎么做？那反正我本来就是对 covariance matrix 去做 eigenvalue decomposition，OK， 所以我可以把每一个 eigenvalue 全部把它写出来，就是 lambda d。OK， 那我每多一个假如这边第一个 lambda 1可能40，OK， 32、5，它会越来越小嘛，因为它是从大到小的过程。OK， 那我觉得这个除上 total 值 ，OK， 那我们这叫 proportional variance explain。那超过90%的话，表示在 overall， 我原本 data 可能假如说我的 data 是 variance 是1，OK， 那我到 K 这个位置的时候，我可能已经解释90% 的原本的 variance， 那我剩下就不要再做 projection， 不要再找下一个 projection， 那我就可以停。那表示你可能就可以你有 10% 的 variances， 我就把它丢掉了。OK， 可能觉得不需要，我其实就只需要这么多的 feature。那你可以从这个图去，对不起，可能这图是实做看看的话，它这个 database 它就是原本有接近70位的 feature。它就 sort 它的 eigenvalues，OK， 然后到20个 eigenvector 这边，那去看它刚刚那个 plot proportional variance explain 到这边大概是90%，OK， 那就可以丢掉。那这个逻辑是怎么样？这个逻辑是说，我的本来的 data，OK， 它本来就有一些变异度 ，OK， 这些变异度很多东西带有重要的资讯 ，OK， 但有可能很小部分是带有噪音而已 ，OK， 所以我可能可以把剩下带有一点点噪音的部分，我就不要再算进来，像10% 的变异度。可能是只是因为我这个收 data 本身会产生的噪音 ，OK， 那我就干脆就不要它了，我就把它丢掉 ，OK， 所以我也不用再把它纳进来 ，OK， 所以透过这样丢掉，我其实可能真正核心的需要的资讯，只有20个维度，而不是原本的60几个维度 ，OK， 好，我想我时间差不多先讲，我再做点总结，因为 PCA 先讲部分，我后面还讲个 再讲个 factor analysis，OK， 他们其实都不难，但我觉得在 concept 上面大家会有点疑惑 ，OK， 但是大家想清楚就好。其实我觉得从这个找到一个新的空间去表达原本的 feature 这件事情的角度要想好 ，OK， 因为这个其实很重要。这个延伸到近代的 machine learning 或 deep learning， 其实也在做同样的事情 ，OK， 就是我如何对原始的 feature 找到一个新的空间对它做表达，让我后续的任务做起来比较准。OK， 或者比较快，或者比较等等之类。OK， 那 这个其实是一种手法嘛，你想这是个什么手法？我就说 OK， 我的原本 data x1、x2，OK， 抓来它分布长这样子 ，OK， 我想要换个角度看它，我换个角度看它，我怎么换个角度看它？我可以说 OK， 其实我想换的角度是我想重新形塑这个 axis，OK， 原本我是个2维的 axis 是这样的 axis， 我在这个2维 axis 看它，它会长这样子。我如果换一个 axis 看它 ，OK， 它会长这样子。那我怎么选择是让它变成这个样子？是一个00 ，OK， 然后两个 Z1、Z2 是 orthogonal， 然后 Z1 带的 variance 资讯又比 Z2 大，如果再加一个 Z3 也要 orthogonal， 但 Z3 不会带的 variance 比 Z2 跟 Z1 大。这整个逻辑的过程就是 PCA，OK， 所以他在找一个 projection 的一个 matrix， 让我可以找出这样子的一个投影到这个方向上面去。这个方向上面的条件就是我要 maximize 那个跟下一个投影的位置它要是 orthogonal， 然后我去找出，所以我就从原本 x1、x2 我乘上这个 w 之后，我的 feature 就会长这样子。OK， 我们下次会教另外一个逻辑是，我如果假设我的 feature 是因为这个才变成这样 ，OK， 那我可以回头找另外一个 projection matrix 把它找回来 ，OK， 这是另外一个想法 ，OK， 不过这概念很抽象，但我希望我都会讲清楚一点，因为这个跟近代的一些 machine learning 比较有关系 ，OK。不过没关系，我们先讲 dimensional reduction， 我就这样子投影过去的过程，然后我这边很多维度，最后我就找几个维度让它变成是这样子。然后最后给大家讲的是，如果看这个 ，if you look at this， 这个有个好处，因为当你换了一个视角 ，OK， 你的 feature 现在的表达变成是在这个空间的表达。第一个维度在这样，第二个维度在这样子 ，OK， 第三个维度的时候 orthogonal 可以去长下去。所以我在这样子的 feature 当做我的 input to my classifier 的时候，你确定它是 orthogonal， 它是 independent。所以我如果用个 multivariate Gaussian distribution 来做 parametric classification 的时候，我可以很大方的使用 diagonal matrix。因为你保证一定是嘛。你 PCA 完后，你保证你的 feature 跟 feature 之间一定是 orthogonal， 所以你不用去假设你的 feature 跟 feature 之间是 orthogonal， 因为你的动作让它不得不 orthogonal。OK， 因为你找这 PCA 过程是用 eigenvalue decomposition 做那 covariance matrix 的 decomposition， 所以 eigenvector 彼此之间它会导致它的象限是正交象限，所以它一定是 orthogonal， 它一定是 uncorrelated， 所以它的 covariance matrix 势必没有 off diagonal 项，所以你势必可以用 diagonal matrix， 所以你就可以用naive Bayes去做事情。所以我如果很多的feature 进来做一轮 PCA， 然后我就可以很大方的输入 naive Bayes classifier， 因为我知道我这样的做法绝对符合 naive Bayes 的先决条件。OK，so that's a trick we can play。OK， 就是你换了一个视角，其实事情就不一样了。OK， 你就可以重做。那这有好多个好处啊，你可以降维 ，OK， 你可以重塑你 feature 的样态 ，OK， 那这个 feature 样态可能可以比较少，可以比较多，没办法比较多啦，比较少 ，OK， 会少到一定程度 ，OK， 然后你还可以结合你原本对于你 classifier 的一些想法 ，OK， 那我们先停在这边 ，OK，I'll continue on Wednesday。Yeah.
Frequency, it can be viewed as an open circuit, okay, assuming, for example, the current is equal to a sine wave. Then we have the voltage is also equal to a sine wave. Where it is proportional to the frequency omega. So as omega approaches infinity, we have this voltage approaches infinity, which can be viewed as an open circuit. Okay, so the current through an inductor does not change abruptly, meaning that if the current changes very fast over an inductor, it will have a voltage approaches infinity, which is not realistic and not an ideal case, which is something we would like to avoid. 电感的电感两端的电流值。好，所以如果它连接到一个电流源，或者是其他提供它电流的元件，这个电流不能有瞬间的变化。瞬间的变化会让它的电感值变成无限大。好，那这是我们要避免的。那电容的话呢 ，for capacitor, the voltage across capacitor does not change abruptly. Otherwise, there will be infinite of a current going through a capacitor. Okay, to summarize, this is just for your reference. The IV relationship of R, C, and L. 这个都是你要记得哈，记得的 I 跟 V 的关系。The power and energy. Remember, power is always equal to V times I, and then energy is equal to the integration of power. Okay. So for a resistor is equal to I squared times R, the power, and then energy for capacitor 1/2 CV squared. For inductor 1/2 Li squared. If we have resistor in series, the total resistance is equal to the sum of each resistors. And then we derive this equation, this relationship for capacitors if we have a few capacitors in series. 对吧？我们有推导，如果有多个电容并联的话，最后的这个等效电容会是每一个的导数相加分之一。好，那电感的话会跟电阻一样。好，所以如果我们有多个电感串联在一起，那它就等于是一个等效的电感，这个电感值是3个电感值相加，这样子。如果它们是串联的话，并联的时候，它的形式也跟这个电阻是一样的。好，如果我们是 DC 的 steady state 跟 high frequency，HF means high frequency. Resistor remains the same. It represents the same resistance, whether it's at a low frequency at DC or high frequency, where the capacitor act as an open circuit and an inductor act as a short circuit in DC steady state. 这个是 dV dt 等于0，所以我们的电流等于0，所以它相当于是断路。好，这个 dI dt 等于0，所以电压等于0。好，电压等于0相当于是短路。OK。高频刚好相反。好 ，continuity for a resistor. For a resistor, we don't have any restriction of its continuity, so its voltage or current can change instantaneous at any time. I mean, it can change abruptly. 对于你的这个电阻，它在上面的跨压或电流可以瞬间有很大的变化，这是没有关系的哈。它的电压变化，电流就跟着变化，不会造成无限大的电流或电压。对于电容来说，the voltage across the capacitor need to change continuously. 好，不可以瞬间从一个很低的点跳到一个很高的点，或者是从一个高的值降到一个很低的值，它需要 gradually changes. Okay. And then for inductor, the current through the inductor cannot change abruptly. It needs to change continuously. Okay, we'll stop here for today.